Welcome to topic 8.5, electric flux, daily video number 1. In this video, we will define electric flux and explore its application through planar areas. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. So before we get going too far into the physical definition of flux, or the physics definition, let's talk about how flux might be used in your everyday speech. For example, if there's an influx of people, they're all going into a particular area. If there's an efflux, it's fluids flowing out of an area. And unfortunately, if there's a reflux, it means things are going back into the area that they came from. So flux is something that's around, but in physics, we have a particular definition of flux. To help us with that, we also have to define what areas are. Areas are defined perpendicular to the plane of the surface, outward from the closed surface. Now, we're going to talk more about closed surfaces in a future video, but for now, just know that whatever surface you pick to be the outward surface, that one, no matter how you rotate it, is going to be the direction that that area vector is going to be pointing. So you pick it, but you have to be consistent through the entire problem. And we'll talk about more about closed surfaces in video 2 in this particular topic. So let's hop into a little bit of review of dot products. Dot product is a vector operation that results in a scalar product. Oftentimes, if you have a dot b, it's going to be ab cosine theta, looking at those magnitudes of a and b. But what is it? Conceptually, it's if you were to take these vectors, a and b, and you were to project a onto b, like that. So I have this angle theta between the vectors. I have this projection going down, and this little section right here, this purple line, is a cosine theta. So really, when you look at it, a dot b is really what they have in common, a cosine theta times b. Well, wait, that looks familiar, because if we manipulate that around, isn't that just ab cosine theta, which is the definition of our dot product? So sure enough, this is what we're looking for when we say dot products. Well, there's a couple key ideas. One of them is that they're maximized when they're parallel. This kind of makes sense, because if it's how much they have in common, they're both fully in common when they're parallel with each other. So that's just going to be cosine of 0, which is 1. And that's going to make it be so that a dot b for parallel vectors are just a, b. But if they're perpendicular, they're 0, because they have nothing in common. You can project a down and you're going to get 0 length. So sure enough, when you plug this in, just cosine of 90, it's going to cancel out. But conceptually, there's nothing projected onto b. Therefore, our dot product is going to result in 0. So now that we've defined those terms, let's look at electric flux in particular. Electric flux is an electric field through a given area, and it's defined as flux is equal to E dot A, our E field dot our area. Or if we expand it, our EA cosine theta, because we're just expanding that dot product term. What does this look like conceptually? Well, here's our area vector through some generic surface, and here comes our electric field through that surface, where my theta between these two would be 0. So we have our term here that is electric flux, measured in newton meters squared per coulomb. We have our electric field, measured in newtons per coulomb. We have our area, measured in meters squared. And we have our angle between the area and the E field vector, which in this case is going to be theta. We'll explore some of that a little bit more. So just conceptually, just to review what we did last slide, is this an example of maximum or 0 flux? Yes, this is maximum. Look at all those electric field lines going directly through that area. If this thing was going directly that way, no one would go through it. Think of it like a doorway to a classroom. People are actually influxing or effluxing if they're going into or out of the room. If they're just walking by in the hallway, there is no flux. So we have to have things going through our given area. And that's what we have here. This is our maximum flux, because theta is equal to 0. Well, let's review what this angle looks like. So now I have my area put at a little bit of an angle. Now I have my electric field traveling through. So what happens in this case? Well, if we look at this, this is the angle that we're referring to, is the angle between our E field and our area vectors. So what can we change in this particular case to make our flux become negative? We already saw how it can be maximized in 0, but how can we make it negative? Ponder that. If this is our original picture that we had, one thing we can do is switch the direction of the electric field. We can make it go that way to the left, while the area vector is pointing to the upward and to the right. That's going to make them have a negative flux. Also, we can rotate the surface by turning that thing all the way around, and that's going to make it so once again the electric field and area vectors are pointing opposite directions. Sure, there's an angle there too, but the projection, if I projected A downward, the projection is pointing to the left, where the electric field was going to the right. So let's look at an example to kind of help visualize this a little bit better. In particular, we wanted to see how changing the area can affect our setup. What's one thing that we can change about the area? Well, if we have this big area with all these little dots that are representing my electric field, if I reduce it Sure enough, I'm going to go from 42 dots to 8 dots. Having a smaller picture frame has less electric field traveling through it. So decreasing the area is going to decrease our flux. One thing just to be aware of is if you have a circular area, if you half the radius, you're going to have 1/4 the area. So always look out for that if you see a problem with the circle. Okay, let's talk about how we can change the electric field magnitude, right? If I decrease the electric field from this many dots to that many dots, sure enough, that's also going to decrease the flux. I have fewer dots traveling through my picture frame. Okay, what if we change the angle? This one's kind of fun. So we have this one that's currently at 0 degrees. And I made this little chart so you can count if you want to, but just kind of take my word for it. We have that one there. If we go to 30 degrees rotation, there's about 35 dots. If I go to 45 degrees, there's about 28 dots. If I go to 60 degrees, I have about 20 dots. And at the very end, if I go to 90 degrees, I have no dots. So here's the thing, the flux clearly decreased, but it's not linear. Let me show you. If we look at our different slides here, kind of as it goes through, there seems like there's not much of a change at the beginning, but there's a big change here at the end. If that's what you're thinking you're seeing, you're not wrong. If we graph this, we get something that looks kind of like this. Definitely doesn't look linear. Well, what does it look like? Well, let's see. If we have this little curve that kind of hops in there, what function is it being? Oh my gosh, it's this cosine of theta. This isn't EA theta. This is the E field, the area, the cosine of the angle theta. And sure enough, this is a cosine function. If we kept on going, we'd eventually start getting some negative areas, and we would just keep the cosine function going around that way. So the brief question kind of posed to you, what angle is half of the initial flux? Yep, it's going to be a 60-degree angle, because right now we're starting with about 42, then we get to about 20. So if you thought, oh, maybe 45, 45 is not going to be the halfway point. The halfway point is going to happen at 60 degrees because the cosine of 60 is 1/2. So what should we take away from this video? Probably one of the biggest things we should take away is what a dot product is and when it's maximized versus minimized. It's maximum when they're parallel, and it's 0 when they're perpendicular. Just kind of a quick thing to kind of have in your brain. Also, area vectors are always defined perpendicular to the surface, pointing outward from whatever you define to be the outside surface of the object. We know what electric flux is, which is just the dot product of the electric field and the area. And then we can change the flux by changing its area, electric field, or the angle. So with that, I look forward to exploring flux a little bit more in the next video, and I thank you for watching this one.